In 2013, a gas giant exoplanet called WASP-75b is identified by K2 satellite using the transit method. Using the public data collected from the extended K2 mission of Kepler Space Telescope, data called corrected light curve can be read by software prop.ly and Excel. Then some manipulation can be done to obtain an image of normalized light curve. Based on the normalized light curve, the total transit time, full transit time, and the depth of the exoplanet can be calculated. In fact, the total transit time, Tt, represents the duration from the first contact, T1, to the fourth contact, T4, which is the time elapsed of the exoplanet first touched the edge to when it leaves the edge of the host star. It has a value of 2.664 hours, and it suggests that the exoplanet transits with an orbit very near to the center of the host star, but not perfectly aligned with an orbital inclination slightly less than 19 degrees. It also implies the moment the ingress star and the egress end, and they can provide information about the exoplanet's size and atmosphere. The full transit time, Tf, is the time duration from second contact, T2, to the third contact, T3, which means the period that the exoplanet is completely in front of the host star. It has a value of 1.9998 hours, and it implies that the exoplanet should be moderate in size and larger than the host star. It is likely that the exoplanet is a gas giant, and these information are crucial to measure the depth of the transit line curve. The depth is equal to the ratio of the exoplanet's area to the host star's area that responds to the brightness of the star as the exoplanet approaches in front of it. Its value is 0.0091, and it means that 0.91% of the star's brightness is being locked during the transit. It supports the suggestion that the exoplanet would likely to be a gas giant of a sub-Jupiter or Neptune size if the host star is Sun-like. The amplitude radial velocity k is the maximum variation in the radial velocity of its host star along the line of sight due to the gravitational influence of the orbiting planet. WASP-75b has an amplitude radial velocity of 146 plus or minus 4 meters per second. It means that the host star moves towards and away at a speed of 146 meters per second. This value is relatively big since it is larger than most of the hot Jupiter. It suggests either that the exoplanet is massive and it is like a gas giant or a brown dwarf rather than a small terrestrial planet, or the exoplanet orbits very close to the host star. For an exoplanet, the stellar property represents the characteristic of its host star. Knowing information about the host star is crucial to understand the characteristic about the exoplanet. With several calculations, the stellar effective temperature, stellar mass, stellar radius, and the stellar luminosity can be obtained. In fact, stellar effective temperature is the temperature of an idealized object able to absorb all incident radiation that would emit the same total amount of energy per area as the host star. It represents the average temperature of the host star's photosphere, and it can determine the star's color, luminosity, and spectral type, which are the factors that influence directly the exoplanet's formation, environment, and potential habitability. For the host star of WASP-75b, it has a value of 6,100 plus or minus 100 Kelvin, and its true effective temperature is between 6,000 Kelvin to 6,200 Kelvin. With this effective temperature range, the host star has a color between white to yellowish white. It should be slightly whiter than the Sun that has an effective temperature around 5,778 Kelvin. In fact, a whiter color indicates that the host star is more hot, more luminous, and emits more energy than the Sun. It means that its habitable zone is farther out and nearby exoplanets receive higher radiation, which affect the orbiting exoplanet's atmosphere and provide a shorter lifespan that limit the time for the development of life. Its possible spectral type should be a late F type main sequence star or an early G-type star. This category supports the prediction of a hot and massive host star and the limit for the development of life since the high temperature fused the hydrogen into helium in its core. The stellar mass is the total amount of matter of a star, and its unit of measurement is in solar masses. The host star of an exoplanet has a value of 1.14 plus or minus 0.07 solar mass, which means that the star has a mass of 1.14 times the mass of the Sun, and it is slightly more massive than the Sun. A more massive star will have a stronger gravitational pull, and its orbiting exoplanet has a shorter period with its stronger gravity. A more massive host star will also emit more radiation and more energy, such as ultraviolet and visible light, which affects the atmosphere and heats up the exoplanet's surface's temperature. They tend to have a moderate magnetic activity. As a result, they provide a more difficult condition suitable for the formation of the liquid water, and they make the exoplanet's habitable zone farther away from the host star. At least the habitable zone is farther out than a Sun. As a result, it has a shorter lifespan for the development of life, and it has a lifespan around 7 to 8 billion years. The stellar radius is the distance from the center of a star to its surface, and it is measured in solar radii. The host star has a value of stellar radius of 1.26 plus or minus 0.04 solar radii. It suggests that the host star is 26% larger than the radius of the Sun. The stellar radius is important for its orbiting exoplanet because a star with a larger radius emits more energy, which shifts the habitable zone of the exoplanet away, and it will have a shorter lifetime on the exoplanet. Stellar luminosity is the total energy emitted by a host star emit per unit time in form of the electromagnetic radiation. It determines the star brightness seen from Earth, the star evolution stage, and the habitable zone around the star. It is typically measured in the unit of sun's luminosity, where one sun's luminosity equals to 3.828 times to the 10 to the power of 26 volt. The host star of WASP-75b has a value of 7.55 times to the 10 to the power of 26 volt. It means that the host star emit around 1.97 times as much as the radiation as the Sun, and it is around twice time more energetic than the Sun, and it supports the idea that the orbiting exoplanet has a shorter time for the development of life. Planetary orbital period is the time it takes for a planet to complete one revolution around its host star, and determine the distance between host star to the exoplanet, its classification, and its equilibrium temperature. For WASP-75b, the planetary orbital period value is 2.30 days. It means that every 2.30 days on Earth are needed for an exoplanet to complete one orbit. A short planetary orbital period implies strong stellar radiation. It can suggest that there is an extreme high surface temperature, a loss of atmosphere, and tidal locking. Since 2.30 days is a very short orbital period, it also implies that the exoplanet is really close to its host star, and if it is a gas giant, it can be classed into the category of hot Jupiter, and if it is rocky, it can be seen as a ultra-short period planet. Using the semi-major axis A, the mean distance between the Sun, or the longest axis across the ellipse that has a value of 0.03750, an equilibrium temperature of 1554 Kelvin can be obtained. This temperature suggests that the exoplanet is extremely hot since it's close to the host star, and it also proves the suggestion that the exoplanet is a hot Jupiter or a highly irradiated gas giant. The impact parameter B is the minimum projected distance between the center of the star and the center of the exoplanet during a transit. In other words, it measures how centrally an exoplanet transits in front of its star. The range of the value B is from 0 to 1. When the b equals to 0, the exoplanet transits directly through the center of the host star. When the b is between 0 to 1, the exoplanet transits partially through the center, and when the b is bigger than 1, there is no occurring transit. The exoplanet miss the host star entirely. And in the context of WASP-75b, the impact parameter has a value of 0.58. It suggests that the exoplanet has a transit that does not occur in the center. It crosses the center with 58% portion of the star's disk. The transit is partially on center, and it is slightly shorter than a central transit, which means that the ingress and the egress phases will be longer than a full phases. And it is also a little shallower than a central transit, and the dip will be relatively less as the exoplanet blocks less host star light. An orbital inclination I is the angle between the exoplanet's orbital plane and the host star equatorial plane. When the orbital inclination equals to 90 degrees, it means that the exoplanet passes directly in front of the host star with an edge-on orbit. When the orbital inclination is less than 19 degrees, the exoplanet passes partially the center of the star. When the orbital inclination much less than 90 degrees, the exoplanet does not transit. And in the situation of WASP-75b, the value of the orbital inclination is 84.84 degrees. It falls into the category of less than 90 degrees, and it suggests that the exoplanet transits as the center of the star, but not perfectly through the star. The planetary mass is the total amount of the matter in an exoplanet, and it can determine the gravitational influence on the host star, its internal structure, and its atmospheric retention. The obtained value for this parameter is 1.97 times to the 10 to the power of 27 kilogram, which is equivalent to 1.04 times the mass of Jupiter, or 329.9 times the mass of the Earth. It has a mass relatively bigger than the mass of Jupiter and a mass much bigger than the mass of the Earth. And the massive exoplanet has a strong gravity, and it can affect its surrounding planet and its own atmosphere. This value also implies that the exoplanet is a gas giant. It should be composed mostly of the hydrogen and helium, and it should have a thick atmosphere with no solid surface. In terms of its internal structure, it should have heavy metals such as rock and metal, layer of metallic hydrogen, and molecular hydrogen and helium. The planetary radius is the distance between the center of the exoplanet to its outer edge, and it determines the exoplanet's physical size. The obtained value of 0.117 or 81,797.39 kilometers suggests that the exoplanet has a radius of 11.7% bigger than the radius of the Sun. It means that the exoplanet has a bigger radius and a bigger size, and then a larger exoplanet can produce a deep transit, and it can block more and more host stars' light. In addition, this value is in the range of the planetary radius value for a gas giant, and it may also have an extending atmosphere, and this can be difficult for life to develop for an habitable zone. Orbital eccentricity measures how circular or elliptical the orbit of an exoplanet is. In range from 0 to 1, when the E equals to 0, it means that the orbit is in a perfect circle. When the E is between 0 to 1, it means that the orbit is in an ellipse. And when E equals to 1, the orbit is open and unbound with a parabolic trajectory. When calculation, the value of the orbital eccentricity is 0.055. It suggests that the orbit of the exoplanet is relatively elliptic, and the distance between the exoplanet and the host star for the orbit remains mostly constant. This kind of orbital implies that there is a consistent stellar radiation, and it can lead to a stable temperature. So there is a minimal seasonal temperature variation over the exoplanet's orbit, and the transits that occur at a regular and predictable interval. The planetary volume is the total three-dimensional space occupied by the exoplanet's surface. Its calculated value of the planetary volume is 2.29 times to the 10 to the power of 15 cubic kilometer, and it has a larger than the volume of the Jupiter, which is 1.43 times to the 10 to the power of 15 cubic kilometer. This big volume confirms that the exoplanet is a gas giant, and it is likely that it has a thin atmosphere. With the value of the mass and volume, the planetary density can be calculated. The density value measures the amount of a given mass packed into a known volume, and it gives information about the composition of the exoplanet. In fact, the calculated value of the density is 0.986 gram divided by centimeter cube, and it can be classified as a lower density value since it has a density lower than 1, and it supports the idea that the exoplanet is mainly composed of hydrogen, helium, and a small amount of heavy metal. The habitable zone refers to the range of the orbital distance between the exoplanet and the host star at which the temperature and atmospheric pressure will allow liquid water to exist on an exoplanet's surfaces. The habitable zone is mostly divided into three categories: inner edge, center, and outer edge. In fact, the inner edge is the closest distance where water on exoplanets remain liquid at the warmest part of the habitable zone, and it has a calculated value of 1.050. The center is the optimal distance for liquid water to exist. It is an ideal location for the development of life, and it has a calculated value of 1.400. And the outer edge is the most outer limit where the liquid water remains at the coldest part of the habitable zone, and it has a value of 2.490. When the exoplanet is within this range of habitable zone, liquid water can exist on its surface, and life has the potential to develop, assuming other parameters are possible. In fact, the planet has a lower density of 0.86 grams divided by centimeter cube. This suggests that the exoplanet is a gas giant. It is mainly composed of hydrogen, helium, and a small amount of heavy metal, and there is no solid surface, so this leads to the difficulty for life to develop and shape. And since the temperature is really high, its atmosphere is really hot. And also, as we classify it as a hot Jupiter, it can experience extreme heat and intense stellar radiation, which can lead to strong atmospheric heating and possible atmosphere expansion. And the exoplanet's orbital eccentricity has a value of 0.055, and this value suggests that the exoplanet experiences stable temperature conditions. And while the gas giants themselves are not habitable, their presence can influence the habitability of other planets in the system. To make an inference on the planetary atmosphere, spectroscopic observation during the transit and eclipse is needed to determine its composition, such as HO2, CO2, CH4, Na, and K, as different molecules absorb light and specific wavelength. Temperature and pressure measurement using remote sensing technique can help to determine the thermal structure and potential for cloud formation. Understand atmospheric dynamics, including wind speed and circular pattern, provide insight into climate and weather system. The seasoning period of a planet can be described by its amplitude, which is the maximum temperature differences experienced across the year. Most dominant parameters that determine the seasoning are the obliquity and orbital period. Increasing the obliquity and orbital period result in a stronger seasonal cycle, such as hotter summer, colder winter, or longer season. Furthermore, change in rotation rate also affect the seasonal cycle. For example, decreasing the rotation rate reduces the seasonal cycling amplitude. This means that as the rotation slows down, both day and night become longer, causing surface temperature change to a more gradual, leading to a more even distribution of heat. Additionally, it increases the latitude shift of the maximum temperature.